Hello everybody, we are working remotely today and I am recording our session kind of in lieu of having regular class. Today is March 23rd, 2020, and if you're listening to this video in the aftermath, which may be the case with some of my future students, perhaps not, but who knows. This is when we were having the COVID-19 outbreak worldwide, and we're basically in a pandemic right now. One of those clauses in our syllabus that we never thought we would have to exercise, but here we are in that situation, and things are kind of scary out there, frankly. Despite that, the school has decided to move just about everything we do online, including the people who work in the offices are all, for the most part, working remotely. Very few people have to go to campus. Because we are in technology programs, we usually transition to these online learning formats a little bit better than other programs. So we have that good fortune working with us because we're basically kind of, geared up for this already and in that mindset. What I'm hoping is that if any of you are having any difficulties working with any of the technology where we're working on sharing our screens or communicating in any way, shape, or form, that you reach out to me and let me know what your issues might be. And even if your issues aren't technological, let's say you have a hard time learning without being face-to-face, and that happens with people, just let me know so that we can make accommodations. The one thing that I do want to make sure that you guys are all clear on, at least for the spring semester of 2020, is that because of our unusual situation, I am going to be kind of foregoing all my late penalties and I'm still going to have due dates, but I'm not really looking at those due dates at this point. We're just using them kind of as a guide as to keep on track as to where we should be progress-wise. There's also some talk here at the school. It has not been formally decided or announced yet, but they're talking about maybe extending the spring semester by a few days or a week, or I'm not sure exactly how long. My inclination right now is that they'll extend it through the week of the 20th, so normally we would end April 20th, and they might extend that out to the 24th of April for the semester. That's not been determined yet. However, if that does happen, you'll notice that it won't affect this class at all. If they extend it further than that, then we might get one extra class session out of it. I guess we'll see. But for right now, we're just operating under the assumption that we're ending on April 20th and that all the things that we do in this class have to be completed by that date. Now, because last week didn't happen, that did throw us off a little bit. So normally I would have had this Unit 6, up for you guys last week, and we would have went to class, we would have talked about it and started working on the homework. And my goal here is to kind of do like a mini version of that today, just to get you rolling on this. Not necessarily the full thing that we would do in class. That might change in this unit. And we're actually kind of backtracking in the book now. We're going back to chapter 3, and we have certain pages that we would like you to read. So it's pages 342 through 351 in chapter 3, and they talk a lot about the relational model and what normalization is as a concept. Normalization in terms of databases is this basic procedure of making the data as efficient as possible in its structure so that the database eliminates largely redundant data and operates more efficiently in terms of the actual operations behind the scene. So if you have less stuff you have to shuffle through to get to the information, of course it's going to work faster. If you have less places where the information repeats, the database will operate faster. And those are really, I think, pretty key concepts. Now normalization is one of those areas where some of you may already be familiar with this concept, but it really is all about that efficiency. Now there's different levels of normalization. Some of them are very practical to achieve, so usually the first few levels of what we call normalization are usually required, I think, by most good database structures in order for the databases to work well. When you get beyond that point, then you start getting into some, I would call almost like theoretical pseudoscience in some ways, where some people who operate very complex database structures look at like fourth, fifth, and beyond levels of normalization in order to make their database optimal. And that's, once again, usually for very large databases with complex designs. And in some cases, some, people in this field almost considered almost like a pseudoscience when you get up to that point, because it's so complicated to get very complex databases to a really high level of normalization. I have included here the PowerPoints for Chapter 3. Now, of course, you guys all have the book, so you can read that on your own. And then there's these PDFs and Christian's lecture notes, which I borrowed from. The PDFs, for the most part, seem to be screenshots of the book, but I don't know if it's from the current version of the book. I assume so. But I think that'll be helpful to just focus on the materials that you need to focus on, rather than plowing through that entire chapter, which at this point is not necessary. The other thing that I put into the course shell here are a couple little guides, basically, and samples. So the first thing that you'll see here is just a really quick little listing of what it is to have good database design. And so when we think about this, and I'm not bringing up a PowerPoint to go through this, I'm just going to kind of talk about it in principle here, is when you're going to build a database and design it, often you're going to be in a few different types of scenarios when you're doing that. So like one scenario is, and I guess from an idealistic standpoint, is that you're starting from scratch. So you have no database structure to work with, you have no information pool that you're pulling from or anything like that, any like pre-structured data, just this concept that you need to build one for some specific reason. So when you approach it from that standpoint, your approach is different than if you were working with something that already existed. And I know that, if you look at the bottom part of this listing here, with these scenarios, basically, I would say more so than necessarily design types. If you're building something that you already have some sort of data on hand. So for example, if you have like spreadsheets that have information, or maybe even handwritten or typed up information that exists, that will give you a different impetus for designing a database than if you're doing it from scratch. And that's the one that I'm kind of talking about right now. Then there's also the scenario where you're rebuilding something that's already been done. But for now, let's just assume this scenario, the new system with no data. We're just, let's say, starting a business, and we're maybe thinking of something simple like a point of sale system and what might go into that, just as a hypothetical. Now, if you start to think about that, you're going to start to think about, well, what kind of data might I collect? I mean, you don't even know yet what you're going to collect, but there's certain assumptions that you can probably make. So if you were doing a point of sale system, the one thing that you would probably want to collect is like the barcodes that go across the scanner, or whatever input the person at the register is typing into the system if they're manually entering information. And then once you get that information kind of organized, then you start to look at what other systems it might interact with. And it would be really logical, for example, for a point of sale system to interact with maybe an inventory system. So every time you get new inventory into your business, you add it to the database that connects to your point of sale system. Then every time you check somebody out, it subtracts from your inventory to show that it's no longer there. That's just an example, a real basic one. But I think that it shows that you would obviously have a connection between whatever you're doing at the point of sale system in terms of tracking sales, and then selling a certain product and then removing it from inventory in a different table. Now, even though we're really kind of only identifying a table or two here, all of a sudden you're already forming relationships between the data just in principle. So you would have to think in that regard, if you're starting completely from scratch, how you're going to tie those things together, what you would design into it. If you were moving instead from existing data, so let's say we take that same point of sale system, and you're maybe working, let's say, with a small business operation that, I think of like my parents' old business where they did everything on paper. They didn't even have a cash register. They just had a receipt book and a box for the money. And as silly as that sounds, they operated their business like that almost into the new millennium. And it was later that we added, cash registers and databases and credit card machines and inventory systems. as I moved into running it. And in that case, we had existing data. So I had, maybe not in the prettiest form, but a paper copy of every transaction that ever went through the place. And then I had also ledgers where we recorded all that information, so I could look at that information and make an educated guess as to the types of tables and information I would try to construct based upon the fact that, well, this is the existing data we already collect. We're going to collect that, and maybe we'll add some more, or maybe we'll tie that into inventory, or maybe into a purchasing system, or something of that nature. But you see a different approach in how you're going to build. The other thing that often happens when we're designing databases is sometimes you work with one that's already there, and maybe it's on a low-level database system. And I'm not knocking Microsoft Access, but perhaps it's built on Access or something older. And you can think of older database systems. I'm thinking like when I was first getting into the field, people were using like DB3 and the IBM DB2 software. I'm trying to think of other silly databases that we had back then that weren't really very powerful, but people still use them. In fact, even I think Microsoft Works, which was like a precursor to Microsoft Office, even had a primitive database in there, which was really just a spreadsheet with a form front end. But sometimes you have older, more primitive systems, or you might even have an advanced system and you need to make it modern or move it to a new platform. That will also require that you look at these things, but maybe not on the same type of level. If you're moving from an antiquated database to a modern database, there's going to be a lot of issues. So a lot of older databases, first of all, may not have even used SQL as their query language. They may have had other proprietary or strange tools within them to do that. Most modern database systems, and when I think about this, at least from like the early 90s and beyond, tended to all use SQL on the back end to do their queries. But there were a few like outliers that did not. So that's always an issue. The other thing that you look at when you're redesigning an existing database is what tables they had and how those tables related, which is why it ties in to today's topic. Now, I thought what would be kind of a fun way to do this, kind of borrowing a little bit from what Christian was doing, and without going into PowerPoints and stuff like that, is to take a look at a sample of what we call unnormalized data. And if you follow this link right here in the course, it'll take you to this spreadsheet. And if you guys want, you can follow along and meet me there. It might be easier to look at it on your own screen rather than mine. But if you can see this okay, let's take a look just really quick at this unnormalized table of information and make some educated calls about it. So first of all, I see that they have this table here, and I'm going to give it a click of zoom here just to make it a little easier to read. And so let's look at the columns. They have employee ID, name, date of birth, age, department title, pay code, and position. Now this is a table that contains employee information. Now there's not a lot of detail inside here that really separates out any of the individuals from any of the things that they're doing in terms of being an employee. So let me break that down a little bit in terms of what I mean. When I look at these first few columns here, and just making a really educated guess, I look at this part and I say to myself, well, this looks like personal information to me. So for example, a person's name, their ID number, when they're born, and obviously your age is an extrapolation of that, so it's kind of the same column really. Maybe things like your address, your social security number, phone number, etc. Those would be personal pieces of information that I think in general should probably be stored in a different spot necessarily than what your department and your pay code and all that stuff is. And so when I look at this, I say to myself, this is personal info in these columns, and these other columns, this seems much more like kind of like HR related or department related things. In fact, you might even break it down to even a couple different possible tables that this stuff could go into just by looking at it. The problem here is this. When you look at the stuff that's going in here, you're going to notice that, I don't see anybody in here that repeats. So it's not like we have, John Smith appearing 10 times in this table. That's always a clear indicator of needing to normalize a table. But we do find that some of these things might be more efficient. So for example, instead of like listing the entire department breakdown here, we might choose to use an ID number to refer to department and then have that be placed elsewhere. And I wonder here, what's the difference between a title? I'm going to step you through the process of normalizing on a rudimentary level. So let's just go ahead and go to the next tab here. So he's identifying, and notice with the highlight of those final 4 columns, that we have some repeating data here. Now, you might not look at this and say, well, there's not a lot that repeats here. What's the big deal, right? A couple things repeat a couple times. But yet we do have information that is repetitive. So for example, the IT designation for department, the news, the administration, etc. And then there's also some spots in here where the pay codes repeat, perhaps even the titles repeat, and there might be a more efficient way to do that. Okay, so I'm going to go now that we've identified on this tab that there's some repeating data, a procedure for breaking it down into different tables. So now, you might not think this way initially, but a good database person instantaneously sees this kind of stuff, and it's always based on experience and repetition mostly. But there is some indication here that, if I was gathering an employee's personal information, I don't necessarily have to put all this typed out information into this table. It might be more efficient instead to have columns for department ID, pay ID, and position ID, and have 3 individual columns perhaps in this table with those codes that then refer to these new tables that basically break down our employees into these different categories. So like if you work for a certain department, you get a certain department code. If you get a certain level of pay, if you get a certain title. Now when you look at something, let's say like this, where the pay type. Okay, so what's the big difference if you have a 2-letter code or 1-digit number? I guess functionally not a lot of data difference. But there is an efficiency when you start to work with really large sets of data that you can refer to other tables that then have tie-ins to other tables. And you might not see it with this table because this information is really simple. However, when you get over to either department or title, where you see that it would be a lot more efficient if I had, let's say, a department ID and a position ID, and then I only had 2 little snippets of data. A single number in a database takes up 1 byte of data, doesn't chew up a lot of information, and it's certainly a lot more efficient in storing, each one of these letters takes 1 byte of storage space to store, and depending on how you set up your fields, might take up even more if you're, if it's always grabbing that much of storage space. So it can really make a significant storage impact. So instead of like, if you had 10,000 employees and you put this in there 10,000 times, and this is 1/8 as efficient as putting in an ID number, it doesn't take a genius to figure out that if you have a large set of data, that it becomes a lot more efficient when you just refer to the ID number. And that's really kind of the point here, is to take logical groupings of information and break them down into separate things. Is it silly to create tables that are this simple? Absolutely not. In fact, I think really good database design does this often. So we go from this being attached to each employee's record, right, to breaking out those tables into their own tables, or information into their own tables. And then you end up with something that looks like this. So you see that the information that's listed here is now, okay, now it's not as meaningful for us to read, but we know that each one of those columns, F, G, and H, have their own related table of information. So you can always go look to them and refer. And of course, we would set up, connections between the tables, relationships, if you will, or even constraints in some cases, to make sure that it's tied in. And then, of course, you can write queries that will pull in that information from those other tables to display it in the text format that you're more comfortable with. But the next thing that we're going to notice here is, there's more repeating data in this position field. Now, we really didn't address that one, and it seemed like it was kind of part of this whole structure, but do we see really repeating information here? And not necessarily. Although I'm not sure what he's pointing out to say repeating data. So let's move on to the next one and see what he recommends. All right. So what he's saying here is that what might make a little more sense if people had unique position titles. So for example, in my position here at Gateway, I actually have more than one title, which isn't a fun thing. Most people here tend to have like one particular title. And that title might not necessarily be the same thing as what your job position is. So let me give you an example. If I, as an instructor, generally my position is instructor, but there's instructor of web software development, instructor of data analytics, and then I also happen to have the title of division chair for IT. And what they're saying here is it's possible that people will have perhaps positions that are different necessarily than the department or whatever formal title they get. So for example, I'm an instructor, but that's not exactly my title, so that's why they are doing this. Now, it is possible in many organizations, and I was trying to use myself as an example, nobody here has more than one title, but it's not unusual in organizations for a person to carry multiple titles, and that's just kind of how their world works. Maybe they might be like half of this and part of that, and that's kind of my situation too. So I'm kind of half instructor and half department chair. So this is another way to break it down. The way that they're tying it to the employee then is through the employee ID. But this is considered a good thing. The next thing that we're noticing here too, and I kind of pointed this out earlier as I was looking at this, if you got a person's date of birth, do I really need to have an age column? And the truth is, the way that they derive the age column is through math, right? So the way that we get the content in column E here is by doing the math, basically today's date minus date of birth, and you have that. Now, a smart database person would say, why are we storing that? Is it really functionally useful? And maybe in some cases that's a yes. Maybe depends on, I guess, what you're doing professionally. In other cases, what if this wasn't even calculated? What if this was hard-coded in, God forbid, and yet, let's say you had 1,000 employees and then every year you go through and update everybody's date? That doesn't make any sense. And to me, the moment I saw this, it screamed red flag to me, which was, oh my God, why would you ever even bother to do that? That's silly, right? So the next thing is to also look at the what we call atomic values. So does anybody know what we mean by atomic values? I'll tell you what, I'll pause the video for a second and see if you can Google it if you want. I've hit record again, so nobody chatted over a response or anything. I'm sure you guys are all busily looking this up on the web. But here's what I Googled and pulled back. So this is just straight up from Google, and it says, an atomic value is a value that cannot be divided. In the table shown below, the values in the color column in the first row can be divided into red and green, hence is not in first normal form. So this is where they're describing first normal form. So what they're really saying is, you're really putting two values in here. you're not really putting one value in there, which is the ideal for what a database is. Now, what's really fascinating about this, in the whole definition, and I know that a lot of instructors will say, don't go to Wikipedia, don't pull stuff off the web, but there's a lot of really good information here. So let's just take a really quick look at what this says. It says an atomic transaction is indivisible and irreducible series of database operations such that either all occur or nothing occurs. Okay, so in other words, what they're trying to say is if you have a whole bunch of data crammed into one field, more than what really should be there, it makes it difficult for you to really properly query your database, extract information, and basically to do stuff with your database. And in some cases, some databases will just completely choke on it because they don't know how to handle it. And the next thing I think that's fascinating that they have here is they talk about first normal form, second normal form, and third normal form. And as far as database design goes, in my mind, that's about as far as you ever want to take it. However, there are much higher levels of doing normalization too. All right. And then they have these very formal definitions. So a relation in second normal form, if it is in first normal form and every non-key attribute is fully functionally dependent on the primary key. All right, I don't know if you made any sense of that, but what they're saying is basically that you got to get it to that first normal form first, and then as long as that's the case, then you can take it to the next level. But they're saying that every non-key attribute is fully functionally dependent on the primary key. So in other words, if we're looking at our sample data, everything in the table is directly related to our primary key. So the identifier for the employee is the ID, not the name. The name's got an issue though because we have what we call atomic values, meaning we really kind of need to split those up in an ideal world. And so what you would really switch that to then, if you go to step 5, is the employees are split into first and last name. So now we know which is the first name and which is the last name. There's no mistakes. There's no guessing. Date of birth is unique. The calculated column is removed. This name is tied to the primary key. All of these are tied to the primary key. They're also tied to foreign keys, so that each entity is completely unique. We've split the tables out into their various formats. We have the position table, which isn't necessarily tied in there. I'm not sure why it wasn't listed on that last slide, but I think you guys get the picture here that we're moving away from basically this, I'm trying to get to that first, unnormalized table. Not that the information is bad, but it's inefficient. It doesn't seem that way when we're working with a small set of data, but as soon as you get it into a really large format, you're going to start creating so much redundant information and slowing your database down to the point where it'll come to a crawl almost, because it's so much faster to process these numbers for a database and then connect it to these tables than it is to actually go through the process of putting that text up on the screen. And if you can imagine tables of information that have significantly more columns and significantly more tables to tie to, that problem kind of expounds itself. So part of the process that we go through in designing data is identifying all the data that we want to capture and then trying to figure out how we break it down into logical pieces. And we played a little bit with that when we were doing, looking at that citation exercise that we did, where it's like, what information can we extract from this parking ticket, and what tables do we put it into? And it was kind of interesting to see what solutions people came up with too. I thought that was kind of interesting. I don't think anybody got perfect on it, but a lot of people got close. And frankly, it's not a process that I would say necessarily is natural to think about. It takes a little bit of practice to figure these things out. People that get really good at this and work with a lot of data and work with a lot of databases can earn some really good money when they see how to fix these things. Now, if you can imagine, if you have databases that already exist and you have information maybe in that not efficient format, that one of your jobs as a database person might be to come in and strip that information out, come up with the extra additional tables and their foreign keys, connect it all together, get rid of unnecessary columns, break apart the atomic data, make sure that all your ID values and your indexes are right, and then you'll have a much, much more efficient database. So one thing that I've heard from several database people that I know is one of the things that they often work on is optimization of databases, and this is where it starts. It starts with the normalization process, that process of making sure the data is logically organized and turned into something that is a little more efficient. So this is, all the steps that we went through to get into what we call first normal form. And actually, he's saying that this is third normal form here on the slides. Well, it's all relative, and I'll tell you why. When we're looking at third normal form here, now we've gotten all of our tables to that level, but initially this was not in that format. So this table in and of itself, I would say, is in first normal form unto itself. It becomes third normal form when we start using these ID values here to make the connections to the external tables, which are also in that form. And hopefully that makes sense. And it doesn't have to be a complicated table to be in that format. All right, I'm going to jump back over to the core shell now. And then the funny thing is we also have a little sample one here that you could look at to try to do kind of some of the same things. Now, normally if we were in class, I would spend some time doing this, but let's just really quickly take a look at this information here and see if we can make some educated guesses about what might not be very efficient here that we might be able to fix. So this is information that is a sales order detail. So apparently we're selling something, and let's see if we can kind of figure our way through the information. So in this first table, we have a sales number, so I guess that might be like a transaction number or invoice number or something. Then we have an employee ID, and it says foreign key, so that ties here, so that these must be the people that were our salespeople, I'm assuming. Then we also have a customer ID, and that ties us down to this table. And then we also have the product ID, so whatever. Okay, so it looks like the sales order details, it's all related to vehicles. So like if you were selling a car, that's where that information would be listed. And then, of course, the date sold. Now, to me, right off the bat, I see some really good design here, and I see some bad design. The first thing that I see that's good is that each transaction has a record number. So that makes it unique. So that's probably going to be our primary key there, I assume. Here we're tying to a different table. Here we're tying to a different table. So I think those are already probably in pretty good shape. Now, the date sold, that's pretty straight ahead information too. What I find as problematic in this table is this column. So if you look at the product ID, and okay, well they got like this VIN number, but it's blank. Here we got a VIN number, and we have a actual model name, and it looks like they're starting to list the features and all this stuff. And right there, just based on this cell alone, it should scream to you the same thing that we saw in the previous example, in that we have atomic data here. So we have a lot of stuff crammed into one cell that really should be separated out. So what you would probably want to do is probably just have, like what vehicle are you selling? You might want to actually have like either an inventory ID number tied to a specific VIN, or you could use the VIN number itself to tie to a particular car. Now, in terms of the way I would design it, the way that I would think is that I would actually have an ID number that's separate from the VIN. True, the VIN is unique, but VINs can also be very long and complicated to type in, and are therefore a little bit more prone for data entry errors, I think. So therefore, a car dealer might only have, let's say, 1,000 cars in stock at the most. A 4-digit, inventory ID seems to make more sense to me, something like that. So I think that's the first area that I recognize as something that needs to break apart. Then I look here at the employee information, and we can see, I can see a number of different issues here. First, they do have some sort of an employee ID, and I think that's good. Starting with single digits, that's a little weird, but it works. Once again, we see atomic data here. First name and last name could be split. I also see that the city field is somehow in error, holding multiple values that should be split across various columns. So that once again we have atomic data that needs to be separated out. So I think that's a pretty easy one to break into these 3 separate columns. I don't see any phone numbers listed. I also see we have a blank column here. I don't know what the point of that is. And then we also have salary. Now, I don't know if HR departments would just, brute force enter data into their tables just like this as to exactly what a person's salary is, but perhaps they do. My thinking is that depending on how it's done, they might actually have a little reference ID here pointing to a different thing. Now, people's salaries can be quite unique, or sometimes they can be quite similar if people are grouped into categories. So I guess the jury would be out on that one. It looks like the commission rates aren't equal for everybody either, and I think that's a little unusual too. But I suppose certain people might get higher commissions based upon whatever their base salary is. Although that doesn't seem to be the case here. You would think if somebody had a low salary, they'd get a higher commission, but who knows what the story is there. Once again, we look at this last table here with the customer information, and once again we see a lot of the same problems happening again, and that is first and last name in the same field, all their address information all in the same field. That could easily be split apart. I also see that their phone numbers in some cases have designations for home, office, or cell, and that can certainly be handled in a better way. In fact, what some demographic tables often do is they'll have separate columns for each, or they might even have a separate table just for phone numbers tied to the customer ID, then adding the fields as necessary. But certainly a lot of combined and atomic data here that could be split apart without a doubt. Now, if you want to take a look here, there's some additional stuff that was added to the bottom. And as an example, so you might actually take a VIN number, and instead of having it all combined in one form, you might actually start breaking it down into the VIN, if that's what you want to use as your primary key. Remember, I argued for the point of using a stock number instead, and having the VIN as kind of like a secondary thing. Then you can break it down into make and model. That makes sense to me, and then whatever features are available, and then you would actually have like a separate feature table that would pull that all in. That would be considered a much better approach to doing it. If you go to the next sheet, and they show a little bit of a breakdown of some of that data, and this is one of these things that once again takes a little bit of practice, and you might decide to do this a number of different ways. So for the first thing that you see is that there was the plan here to split the first and the last name. That's a smart move. It's also probably smart to put in the city, state, and zip. Now some people will argue that, well, if you put in a zip, the zip already implies a city and a state. Okay, so maybe I really don't need to have a city and a state column in my employee table. Although I'm going to give you a scenario where I can show you it doesn't sort of work. And that scenario would be, for example, I live in the 53211 area code. And if I was to Google that online, you'll notice that it covers the city of Milwaukee, and it covers the city of Sherwood. So I can't make a direct correlation between that zip code and what city I live in. So I think that that one can be a little flawed. So sometimes zip codes can cover multiple cities, but I do get the point here that the zip can imply both city and state. It automatically implies state. Many times the zip code is unique to a city. Some cities have multiple zip codes, but some zip codes, like the one that I live in, crosses city boundaries. And so I could be Sherwood or I could be Milwaukee and still have the same zip code. So that one I would watch a little bit, and that would be one where you could have discussions on that too. All right, so that's just kind of my quick little example of how to do the normalization. And believe it or not, for the most part, that is about as much information as you guys need to go out there and get the homework going. The homework assignment that I did post will give you some information. And I do want to point out there's a little correction here. And I just put that in. You guys will see it when you're working on it. But as we do with the other assignments, you'll pull down the document. And in fact, I'm just going to go ahead and pull it down so you can look at it, so you see what you're working on. And so you have that same table of information. And you guys know we're not using the discussion board part of this, but they want you to follow the rules. Now, if you do the reading in the book, and I'm not going to, PowerPoint you guys or anything like that, you guys can read this stuff yourself and you can watch the videos yourself. Our attempt here is to move it from first normal form to what we call second normal form, and then finally third normal form, and then run the following commands here at the end. There's not really a significant amount of work. It's more thinking about it kind of stuff. But I think that it's kind of interesting because the homework assignment does kind of narrow down what first, second, and third normal form are. And it says, in first normal form, the rule is remove any repeating attributes to a new table. So, and it gives you the step-by-step on how to do that. In the second normal form, the rule is remove any non-key attributes that only depend on part of the table key to a new table. All right, and then follow the steps for that one. And then third normal form is to remove a new table any non-key attributes that are more dependent on other non-key attributes than the table key. And so I know the terminology is a little hard to follow when you read it like this, but if you think about the stuff that we just did in the examples, it shouldn't be too bad. And so my thinking here is this is really enough information for you guys to proceed with your work. And rather than stay online with you during this strange little online session and do the work with you, I would kind of rather you guys work on it yourself. And then when we get to next week, I'd be happy to help guide you on any of the issues that you may have had in doing this work, and then guide you on to what is right. But for right now, I think that we're armed with enough information to get working on this, and kind of call it a day. So I'm going to end this video here, and then I'm going to open it up to questions and discussion.